Hello everyone, this is Nav, and today I have this new video on soaring or seed pile design using AASHTO LRFD 9th edition. Before we start, I request you to subscribe this channel for future contents and also help us grow this channel. That being said, let's get started. In this video, I will explain about the design philosophy of seed piles and I will show you how to design it for a real project. For your information, instead of doing hand calcs, I will create a spreadsheet so that it's quicker, and it will also expedite the design process if you are working on a real project. In this diagram, we have a seed pile embedded in the ground as shown in the figure. On the right side, we have retained soil, and on the left side, there will be some excavation, and the last line of excavation is the dredge line. Let's say we have a footing here that needs to be constructed, and we'll basically go all the way to the bottom of that footing, and we'll excavate all that soil just to construct this footing. So a dredge line will be the last line up to which the excavation is done, and the depth of excavation is h, and the embedment from the dredge line up to the into the ground is the depth d. Now let's take a look here. If you look in the right side, I've drawn earth pressure distribution due to active and passive pressure. The first one is active pressure distribution, and the second one is just passive. I'll just wanna make it more clear by separating both of them. And if you look at the active pressure distribution, you can see in the left side we have active on this portion of the soil, which has a depth of h plus x, where h is this depth. That's the depth up to the dredge line from the top of the retained soil. So this portion of the soil is in active, so the earth pressure intensity at the bottom right here will be Ka gamma S plus X. And similarly, this portion of the soil is in active pressure, so it will start from something, and it's not going to be 0 at this depth because we have a depth of X. So this will be Ka gamma X, and the one at the bottom will be Ka gamma D, because this is the embedment depth, which is at depth D. So this is the active pressure distribution in a seed pile, and let's take a look at the passive pressure distribution on this right side. If you look, the passive pressure is at this corner and right here. So let's take a look here. This is at a depth of X, and the intensity at this depth is Kp. It will be Kp because it's a passive pressure, Kp gamma X, and it will start from 0 because this is the ground surface right here. And also let's take a look at this corner. So as you can see, this is at certain depth, and this depth is d plus x. This is h plus x. So the intensity here will be Kp gamma S plus X, and at the bottom this will be Kp gamma S plus D. Now let's take a look at the net pressure diagram. As you can see in the middle, I have combined both active and passive pressure distribution, and I have come up with this diagram. But it's basically the difference of two loads coming, the pressure difference coming from passive and active at each location along the seed pile depth. That's all I want to say for now. And if you take a look at the right side here, and this is the simplified pressure diagram, having a parabolic profile, it will complicate everything. So the best practice is to simplify it using a straight line. We will assume that the pressure distribution is linear, not parabolic, and just simplify our analysis. Since we already talked about making a simplified pressure diagram from a parabolic net pressure diagram, we will go to a different level. We will even make it more simpler. Again, we will make it more simpler by removing a portion of our simplified pressure diagram. I will just say that, hey, it's fine if we ignore the portion below this and just consider just this portion of the pressure diagram along the seed pile. And this is also known as simplified method. When you calculate the embedment depth from this simplified method, you should multiply the depth by 1.2. As you can see in the screen, This is figure 3.11.5.63 from AASHTO LRFD 9 specification, and this is particularly for permanent non-gravity cantilevered walls with continuous vertical wall elements. It's basically for seat pile. As you can see, it has inclined slope, so it looks a little fancy, but it's basically the same pressure distribution, and it's doing the same thing here. We'll calculate D, which is denoted as D naught here, and then to get the total embedment depth, we will multiply by 1.2 D naught. Now let's talk about what we are actually supposed to do. So this is the bridge where we are replacing the whole superstructure and also the substructure. It's a whole bridge replacement, and we have substructure around here, and these are the wing walls, and it's a two-way road with 2 lanes, and this is the divider, just the pavement marking, and the bridge won't be closed completely during construction, so there should be the maintenance of traffic on this bridge, so only half of the bridge will be closed at once. So that's why the soil or the fill on one side should be retained, so that the vehicles can travel over it. This is what I was talking about. I was saying that this side of the road, or it could be the left side, but I'm just taking this side as an example, and this will be maintained for traffic. We will have some barriers somewhere here, but the important point is you should also consider the load that's coming up from the live load, from the vehicles traveling on this side of the seat pile. So we'll also consider that load for our seat pile design. Now let's take a look here. Now I've drawn the pressure distribution, the earth pressure distribution, and also the live load surcharge that's coming from the live load, and we will use this load distribution for our seat pile design. And as you can see, this is the simplified version of what we have discussed before, and this is the additional portion that I have added here, and that's coming from the live load. Let's now talk about different sections in AASHTO LRFD which we will be using for seat pile design. The first one is table 3.4.11, and we'll be using the strength 1 load combination, so we will use load factors for earth pressure. And as you can see, all earth pressure or all earth pressure forces have are in the same column, and they have the load factor of gamma p. And if you look in another table 3.4.12, you can see for horizontal earth pressure, the active load factor is 1.5. The maximum value, we'll be using maximum value for seat pile design. And you may be thinking, what about the passive pressure? It should be noted that for a seat pile, active pressure is the load acting on the seat pile, and passive pressure is actually the resistance, which is supposed to balance the active earth pressure. So the factor that will be used for passive earth pressure will be the resistance factor instead of load factor. Also, the load factor for the live load surcharge is given here. For strength 1, the load factor will be 1.75. So this is table 11.5.71, and it will give you the resistance factor for passive resistance of vertical elements. We'll be using a resistance factor of 0.75, and also capacity of vertical elements, and it is 0.90. We'll use this when we will calculate the section modulus from the maximum moment acting on the seat pile. Refer to AASHTO LRFD 3.11.53 for calculation of active lateral earth pressure coefficient, and you will see we have these two equations. In our project, in our case, from the geotechnical report, we have the effective angle of internal friction is 30 degrees. The friction angle between fill and wall is 14 degrees. Since the fill is pretty much flat, so beta will be 0 degrees, and also since the seat pile is vertical, so the theta angle will be 90 degrees. So when you put these values in these equations, you will get this constant as 2.55, and if you put it here, you will get it as 0.303. So this is how you calculate the active earth pressure coefficient. And now we will move on to calculate the passive lateral earth pressure coefficient. So in our case, we have internal angle is 30 degrees, so we will use this line as a reference, and theta is 90 degrees in our case. And then when you just go up and you will meet somewhere out here, that will be 6.5. If you come here, that's nearly 6.5. And but there is a reduction factor for various ratios of delta and the internal delta and the friction angle. So we will also correct using that reduction factor. We'll just multiply 6.5 with whatever we get from this table. So for delta by phi, we have 14 by 30, and this is 0.47. And from above table, if you interpolate these values right here, you will get the reduction factor as 0.728. And if you multiply 6.5 with 0.728, you will get 4.73. So this will be our passive earth pressure coefficient. Let's talk about live load surcharge on a seat pile. In our case, traffic is moving parallel to the seat pile. We'll use AASHTO table 3.11.642, and you can see for any depth, if the distance is 1 feet or further, the equivalent height will be 2 feet. For the live load surcharge, you can refer to equation 3.11.641 of AASHTO LRFD 9, and you will see this equation up here, which is the constant horizontal earth pressure due to live load surcharge, and it says delta H equals to K times phi of soil and its equivalent height. We already got this height, which will be 2 feet, and this is the unit weight of soil, and K is the lateral earth pressure coefficient. And it doesn't say if it's active or passive, and the reason is because it depends which side of the seat pile the traffic is on. In our case, the traffic is on the active side, so we will use the active pressure coefficient in our case. Now let's do some derivations so that we can use these equations for our spreadsheet. And basically I'm gonna need the intensity A at this depth, which is basically the active earth pressure. And if we use the strength 1 load combination, I'll be using load factor for EH times Ka gamma H. And now I will calculate B in the similar manner. B is the intensity at this at the bottom of the seat pile, which is basically the difference between the active earth pressure and passive earth pressure. So the active earth pressure at this point will be EH is the load factor, Ka gamma, and the height will be H plus D minus. And for the passive pressure, we will use resistance factor phi, which is 0.75 times Kp gamma, and it will basically be this side. So it is gamma D. So that's B. And now let's talk about how we can find dimension X. At X, at X depth, the active pressure and passive pressure are same. So the active pressure is EH Ka gamma H plus X is equals to passive is phi will be the resistance factor for passive, Kp gamma times X. So if you calculate X from here, it will be EH is the load factor for EH load, Ka gamma H divided by phi Kp gamma minus EH Ka gamma. So this is all the equations we'll be using. We'll be using X, the equation for B, and the equation for A in our spreadsheet. And one more, we'll also be using this live load surcharge equation. So let's calculate the value of C. So C is the live load, so we'll be using the load factor for live load, LL, which is basically 1.75, as I discussed with you already, times it will have Ka because it's in the active side, then gamma, and H will be the height equivalent. Let's now move on to the spreadsheet. I will be using the spreadsheet, just to expedite the process of the design. We already talked, theoretically, I explained a couple of things that will be needed on this spreadsheet, and I already showed you how I got these numbers. If you have any questions, please watch my video again, and make sure you understand each and every numbers up here. And also, I'll be using the same equations here, so feel free to watch my video back and forth and whatever you need. Um, the depth D is what I want to calculate, but I don't know yet. So I will just put a random number, say 10 for now. I'll be iterating this number, and I will find the correct value. I'm going to use a couple of tricks, and I will explain you what I'm going to do. But for now, just assume the value of D, the embedment depth, is 10 feet. And the value of A is the intensity of Earth horizontal pressure at this point right here, as you can see in the screen, at a depth h. So that's basically the intensity of active Earth pressure at depth h. And since we're using the strength combination, strength 1 combination, we'll use the strength 1 load factor as well. So the equation for A, as I already explained to you, is EH, this is load factor, times active earth pressure coefficient, Ka, times gamma, which is the soil unit weight, multiplied by the height h, and enter. And the unit is in kip per feet square. So because it's along the seat pile, which is continuous, so we'll be assuming 1 feet of seat pile, and the intensity is in kip per feet. So the overall unit is kip per feet, and or you can say kip per feet square. Now let's calculate the value of x, and x is equals to parenthesis load factor for EH times Ka times gamma times h, parenthesis closed. Then we have phi for passive, Kp multiplied by gamma minus EH for active, K times gamma. And we got 1.32. And the unit is feet because it's basically the distance from the dredge line. Now let's talk about how to calculate B and C. I already calculated B and C so that I can save some time, but I will go through the equation that I've used here. So B is the point, the intensity up at the bottom of the seat pile, and you can see it's in the other direction. It's the passive pressure, so it's coming as negative. So what I'm basically doing is I'm using the the active force, the active pressure subtracted by we'll subtract the passive from the active pressure, and the value is coming as negative because obviously the passive pressure will be higher at the bottom of the seat pile. I'm using the load factor for active pressure, which is EH 1.5 multiplied by C3 is the Ka, and then we'll use gamma, and then the depth will be H plus D, which is C2 plus C8 H plus D, and then I'm subtracting the passive component, which is the phi, that's right here, and then C4 is Kp, and then gamma, and C8 is the embedment depth because we don't have passive pressure coming all the way from the top, it's coming from the dredge line, so we're using depth D, and that's how you got B. And for C, we're looking at the live load surcharge pressure diagram. It's coming all the way from the top. So the total depth is D plus H, and the value of C will be, if you look here, that's the live load, so the factor is 1.75, and it will use, we already discussed about this in AASHTO LRFD, so it will be multiplied by Ka factor, and then C5 is Ka multiplied by gamma times the C6 is the H equivalent height, which you will get from AASHTO table using the depth of H plus D. So this is the value of C, and it's in kip per feet square, and it's very important to understand that this load is distributed for the depth of for the height of S plus D. Now let's take a look at these pressure diagrams. So we are considering the triangular portion as area 1, and the one below that is area 2, and the one at the bottom is area 3. And in this pressure diagram for the live load surcharge, we will consider that area is area 4. So I already have some calculations done here. I'll explain you what I have done so far. The main intention is to find the moment and from the forces and moment arm. So the area of each geometric portions, basically triangles and rectangles up here, will be the force, and when multiplied by the moment arm, we'll get the total moment. What we are considering is we are assuming that the seat pile rotates from its bottom point from the depth d, and it will act as a hinge. So we will be calculating the moment about the bottom. So let's take a look at area 1. So it's a triangular portions with intensity A, total maximum height is A. So this is the height of the triangle, and the base is height h. And so the force will be one half of base into height, which is 0.511 times the height h. So we have 0.5 times c2 is the height, and c9 is the dimension a. So that's how we got force from area 1. And the moment arm will be h divided by 3, because the CG will lie at a distance of h by 3 from dredge line, and and then add depth d to h by 3. So it will basically be c8 is the depth d plus h by 3, which is height 9 divided by 3. And when you multiply both, you'll get the moment. And let's look at the area 2. For area 2, we'll use same height of the triangle a, but the base will be x, which is 1.32. So when you calculate the area, it will be 0.5 times a into x. And the moment arm will be d minus x divided by 3. Yep, so d minus x divided by 3. And moment will be force into moment arm. And let's calculate the force from area 3. So we have b, but we don't have this distance, which is d minus x. So we'll calculate it as 0.5 times d minus x is c8 minus c10 multiplied by c12, which is the dimension b. So the force will be negative because that's the force coming from the passive pressure, and that's why the moment should also be negative. So it makes sense. And the moment arm for this one is, since it's right so close to the bottom, it will be this distance divided by 3, which is d minus x divided by 3. So it will be d minus x divided by 3, and then you get the moment arm by multiplying both. And let's take a look at the area 4. And the for the area 4, the width of this distribution is c. So that's basically c. So the force will be c multiplied by height. Total height is h plus d, and the moment arm will be half of h plus d, which is c8 plus c2 divided by 2. And again, we'll multiply it to get moment. Now we'll get a sum of all the forces, and we'll calculate the sum of all the moments. Now it's very important to understand that the main purpose of seat pile design is to balance forces. Active pressure is the load acting on the seat pile, as well as the live load surcharge acting from the traffic or the live load. But the passive pressure is the one resisting all the loads coming on the seat pile. So the main purpose of seat pile is to balance these loads. We should embed seat pile to a depth where we get enough passive pressure to resist all the forces acting on the seat pile. So at a depth of d, where we get the total moment from all the forces at 0, will be the embedment depth. That will be the minimum depth the seat pile should be embedded to. So what we'll do is we will assume different values of d and try to come up with the moment value as 0. At that depth d, the all the forces in the seat pile will be balanced, and that will be our embedment depth. So let's try that. So I'm using 10 right now, so I'm just gonna do some trials and just try to be as close as 0 for the moment. So let's try 9. So as you can see, it went up from 14 to 22. So I'm gonna go above 10. Coming down, so let's say 12. Now it's gonna go went to negative, so let's say 11.5. Again 11.25. It's pretty close. 11.3. No, it's really close to it. Again, a little more. Yeah, that's pretty close. 0.3. I don't think it will. Okay, so 11.29. It's fine. I'll assume it at zero. So at a depth of 11.29 feet, the moments are, the sum of the moment from all the forces is zero, which means the forces are balanced. So that's the depth I want for embedment. So moment is zero when d is 11.29, right? But as I said, since we are using the simplified method, I will multiply my load, my sorry, the depth that I got from the calculations by 1.2. So it will be 1.2 times whatever I have here. So 14 will be my embedment depth. So 14 feet is the minimum depth the seed pile should be, you know, um, embedded to, so that the soil retained on the other side is stable. Um, but the other thing is, we are talking about embedding seed pile. But what kind of seed pile should we embed? I mean, what should be the cross section? So what we will do is we won't specify any particular type of seed pile, but we will rather give contractors, that option that they can use any seed pile they want, but it should have a minimum section modulus. So what we will do is, we will find maximum moment acting on the seed pile, and you can already, have it in your mind that the maximum bending moment will be at a point where shear force is zero. At that depth, at that distance where shear force is zero, we will calculate our moment, and we will use that maximum moment as our design moment, and we will calculate our section modulus based on that maximum moment. So let's find the depth where the shear force is zero. As you can see in this spreadsheet, I'm getting the sum of all the forces, not the moment. The sum of all the forces is minus 13.88. If I can find the distance d where this force is zero, that will be the location of the maximum moment. So let's do that. I'll just assume, say 8, coming down, maybe 7. Okay, it's going down again, 6.5. Okay, 6.25. Okay, it's pretty close. 2, 4. Okay, 6.23. See, so at a depth of 6.23 feet, the total shear force acting on the seed pile is zero. At this location, at depth 6.23, the shear force is zero. So the moment that I'm getting at that point is 30.95. This moment will be the highest, the maximum moment acting on the seed pile. That's the basic statics. And what we will do is, we will just fill this out. Force shear is zero when D is 6.25, 6.23 feet, and the maximum moment at this point is 30.95. I have this section modulus equation here. So it's basically, since it's in cube feet per feet, so I'll multiply that moment by 12, and then I'll divide it by 0.9 times 50. 50 is the yield strength of the steel material used as a seed pile, and 0.9 is the strength, the reduction factor for cantilever sheet piles. So yeah, as you can see here, we have designed our seed pile. The information that we need to send to contractors is basically the embedment depth of 14 feet and section modulus of 8.25. So this is the only information they need from us, from the structural engineers. So we have done our job, and this is all you need for seed pile design. And finally, hope you guys learned how to design seed piles or temporary shoring today. Thank you for watching. Please press the subscribe button and turn on channel notifications so that you get all new contents. Take care, and I will see you in next video. Bye bye.